Welcome to The Explainer. Today, we're diving deep into an invisible battle, a fight that happens inside your computer every single millisecond. We're talking about the race against chaos. So, picture this. You find the last seat on a flight to Goa. You click book. But at that exact same nanosecond, someone on the other side of the country does the exact same thing. How does the system not just completely break and sell the seat twice? It's not luck. It's a fundamental problem in computer science, where dozens of different programs are all trying to use the same piece of memory at the same time. And without rules, that race would be total, absolute chaos.
And that chaos, well, it actually has a name. It's called a race condition. Basically, it's when the final answer to a problem depends entirely on who gets there first. Imagine two different UPI apps trying to credit your account. Let's say your balance is 500 rupees. Both apps read 500. Both calculate the new balance as 600 and both write 600 back. You were supposed to get 200 rupees, but your final balance is just 600? Poof! Because of a race condition, you've just lost money.
Now, when this happens, it's not just a small glitch. We're talking about corrupted data, system crashes, real problems. The only way to fix it is to manage the race. We need to find that one specific dangerous part of the code, the part where everyone is trying to grab the same thing, and we need to put a guard there. And that protected area, that danger zone, has an official name. As you can see here, it's called the critical section. This is any piece of code that touches a shared resource, a variable, a file, anything. And honestly, a huge part of operating system design boils down to this one simple challenge. How do we control who gets into the critical section and when? So, how do we do it? Well, the operating system basically acts like a bouncer at a club. It sets up a protocol, a strict set of rules that every single process has to follow if it wants to get inside that critical section. Think of it like a room that can only hold one person at a time. The OS is the one at the door, managing the line. But what makes for a good bouncer, right? You can't just be unfair or lock the door forever. As these notes show, any decent solution to this critical section problem has to follow three absolutely non-negotiable rules. And here they are, the three golden rules. First up, mutual exclusion. This one's the biggie. If one process is inside that critical section, nobody else can get in. The door is locked, period. Second is progress. If the room is empty and people are waiting outside, you have to let someone in. You can't just keep the door locked for no reason. A decision has to be made. And finally, bounded wait. This is all about fairness. It means once you get in line, there's a limit to how many other people can cut in front of you. You're guaranteed to get your turn eventually. No starvation allowed. All right, so we've got the problem, and we've got the rules for what a good solution looks like. So how do we actually build something that follows these rules? Well, let's start with one of the oldest, most fundamental tools in the programmer's toolbox, the semaphore. So what on earth is a semaphore? At its core, it's really just a special integer that acts as a gatekeeper. A binary semaphore is the simplest kind. It can only be a 0 or a 1. Think of it like a key to a single room. It's either available or it's not. A counting semaphore is a bit more flexible. It can be any number, like having a stack of 5 keys for 5 available printers in a lab. Now, a process uses two special operations to talk to this gatekeeper. The first one is called wait. This is like asking for the key. The process tries to decrease the semaphore's count. If that count drops below 0, it means all the keys are gone and the process has to wait. The second operation is signal. When the process is done, it calls signal, which increases the count. It's like putting the key back on the hook for the next person. Now, the crucial part here is that these operations are atomic. That's a super important term. It means they are indivisible. They happen all at once and can't be interrupted halfway through. And if you look at the logic behind this, it's pretty clever. When a process calls wait and finds the resource is busy, the OS doesn't let it just sit there spinning its wheels, wasting CPU time. No way. It puts the process to sleep and adds it to a waiting list. Then, later, when another process calls signal, the OS just wakes up the next process in line. It is incredibly efficient. Okay, but here's the catch. Semaphores are really powerful, but they're also kinda dangerous, like a power tool with no safety guard. It's completely up to the programmer to use them correctly. What if you forget to call signal when you're done? Whoops, you just locked a resource forever. That's a deadlock. What if you call them in the wrong order? Suddenly, your protection is gone. There has to be a safer way, right? And there is. The thing about semaphores is that a small mistake can create these incredibly subtle bugs. As these notes say, these timing errors might only happen one time in a million, just depending on the perfect unlucky sequence of events. And for a programmer, that is an absolute nightmare to try and find and fix. So this very real danger of messing up semaphores forced computer scientists to come up with something better, a higher level tool that was safer by design. And that brings us to the next step in our story of taming chaos, the monitor. A monitor is, well, you can think of it like a pre-built safe for your data. It's a feature built into the programming language itself that bundles the shared data and all the functions that can touch that data into one secure package. So where a semaphore gives you the raw parts to build your own lock, a monitor gives you a fully assembled foolproof one. The computer's compiler automatically handles all the locking for you, guaranteeing only one process can be running code inside that monitor at any given time. So why is this so much safer? Well, first off, the programmer doesn't even have to remember to call wait and signal anymore. It's impossible to forget. You can't accidentally touch the shared data without going through the proper channels, because the compiler itself enforces the rules. It just makes everything cleaner, clearer, and way less likely to have one of those nightmare bugs. So let's just step back for a second. The crucial point here is the journey we've taken. We started in this world of pure chaos, the race condition, and we've moved step by step toward more structured, more elegant solutions, where each new idea learns from the problems of the one before it. This timeline really sums it all up. We started with the fundamental problem, the race condition. That gave us a formal challenge to solve, the critical section problem with its 3 rules. Our first real solution was semaphores. Powerful for sure, but also pretty risky. And that risk is what pushed us to evolve to something safer and more structured, monitors. That's the classic story of progress in computing. And you know, this isn't just some abstract theory from a textbook. These ideas, semaphores, monitors, they are the invisible guardians running right now on your phone, on your laptop, on the massive servers that power the internet. They are the reason our incredibly complex, multitasking world actually works without just falling apart into data chaos.
This all connects back to an even bigger idea in engineering, which is captured perfectly in this quote about graceful degradation. It's this idea that a really good system shouldn't just crash when something goes wrong. It should handle failure elegantly. And having proper synchronization is the foundation for that. A system that prevents race conditions isn't just correct, it's robust. It's a system you can actually trust.
Which kind of leaves us with one big final question. Semaphores and monitors were designed for a world with one, maybe a few processors. But now, we're building computers with hundreds, even thousands of cores all running in parallel. Are these tools still enough? What does the next chapter in our race against chaos even look like?